Hello, everyone. Thank you for joining. We're going to start in a minute or two. We're just going to give more people, we want to give more time to people to join. We're going to start in a minute or two. So thank you all for joining. So I think we can get this started. And thank you all again for joining. Today we are hosting Elara Engineering and Don, Brian, and Dustin presenting inspiring and sorry, I think we have Elara Engineering presenting to us today. And I'm going to talk for a couple of minutes about what is CLF, what is the CLF Chicago chapter. Can we go to the next slide? Yeah. So the CLF, the Carbon Leadership Forum Fund, started in 2017. It's a group of architects, engineers, contractors, got together trying to resolve the issue of the embodied carbon in the built environment. And the goal is to create tools, resources, and a network that can help us to decarbonize the building industry and achieve the stringent net zero goal, hoping to reduce the embodied carbon in the materials that we use in the buildings. And the Carbon Leadership Forum, we have the networks and the chapters across the nation. The events that you're attending today is organized by the Chicago chapter. And we have Elara Engineering presenting to us. Next slide. These are our sponsors and partners. And as you can see, the Carbon Leadership Forum is now sponsored and co-organized and co-sponsored by so many engineers and architects across the nation, and is growing every day. And every month we have a new chapter somewhere in the nation, and is growing so fast. The webinar that you're watching today is going to be recorded, and you can find that on the embodied carbon network later on. You can already watch a lot of recorded webinars that happened in the past couple of years. The hope that with all these resources and the recorded session, we can raise awareness and provide education for the for the professionals in the industry. I also just wanted to mention the recent announcement from AIA. The AIA recently announced that they published a series of tools and resources to help architects to stop climate change. This is gonna further accelerate the process of getting to the AIA 2030 commitment and is aligned with the CLF goals and targets of reducing the embodied carbon in the built environment. So with that, with no further ado, I will hand it to Brian, Dawn, and Dustin to present. Thank you.
Thank you, Mohammed. I'm going to start. It's Don McLaughlin. And why don't you go ahead and flip to the next slide, Brian. So this is just a bit of an outline, but what we're going to talk about is how to cost effectively meet net zero carbon emissions, either through on-site renewables or via off-site renewable energy credits. And we thought we'd start the discussion with some of the indirect costs of unsustainable practices. For those of you that have not viewed NASA's website on climate change, both NASA and NOAA, it might be surprising to some to learn that over 60% of NASA's budget is focused on studying Earth. And through satellite imagery and sensors all over the globe, between the two agencies, they collect more data on Earth than any other agency. And what you're seeing there is CO2 levels over the last 400,000 years. And you can kind of see to the right, before 1950, it never gotten up over a line of a little over 300 parts per million. And then there's a sudden spike from 1950 until the current level is slightly over 400 parts per million. So it's over a 33% increase. And scientists almost unanimously agree this is due to the burning of fossil fuels. Flip to the next. So you may ask, you know, when CO2 is measured in parts per million, it seems like a very small number. How can it have such a, how could 100 parts per million, for example, increase have such a significant effect on our environment? But CO2 in the environment acts, it basically absorbs and reflects infrared light that's re-radiated from the Earth being warmed by the sun in a spectrum that is very sensitive. So similar to low E glass, how the metallic film on the inside of low E glass will reflect radiant energy back into the building. CO2 is very effective at absorbing and re-radiating infrared in a sensitive spectrum that is not affected by water vapor, which is another greenhouse gas. And so that's why it sort of upsets the heat balance, if you will, or to create the warming trends that we've seen. So flip to the next one. So this is 17 of the last 18 warmest years in the 136-year period have occurred since 2001. Again, this is all off of NASA's website. Flip to the next one. You can't really explain this from solar irradiance. You can see how irradiance has actually gone down, you know, since 1960 as temperatures went up. You can flip to the next slide. And you can see that Greenland, we're currently losing something like 286 gigatons of ice per year. If you flip to the next slide, you can see in Antarctica it's about half that, but it's still a significant 127 gigatons of ice per year. Sea levels are rising at 3.2 millimeters per year currently and increasing. And some of the excess CO2 is being absorbed in our oceans, which is making them more acidic, which is affecting marine life. You can flip to the next slide. And the climate change accelerating factors as ice melts, blue water absorbs more sunlight. As the ocean temperatures rise, ocean water expands. As temperatures rise, plants do not absorb as much CO2. And it's anticipated there'll be more extreme weather events, includes droughts and heat waves. Sea levels are expected to rise if nothing changed by as much as 1 to 4 feet by 2100. If you could imagine how devastating that'd be to some of our low-lying cities around the world. Next slide. And the question would be, has this ever occurred on Earth before? And fossil records have shown there's a lot of research that has been done on this over 252 million years ago at the Permian Triassic extinction, or the PT extinction, and over 96% of all marine life died, and some 70% of all terrestrial life died as a result of a runaway greenhouse effect that was basically, it's suspected was caused by volcanic activity that released a lot of CO2 gases into the atmosphere. Maybe you could flip. And another factor is the increase in population. Population has more than doubled over the last 60 years. Currently, we're somewhere just under, it's estimated under 7 billion people on the planet. Flip to the next. And so buildings in the built environment, which is what we're going to talk about today, it's estimated that in the US that buildings account for almost 40% of the total energy. So if we're going to solve these emission issues, the building environment is a big piece of that pie. You flip to the next. And so often an overlooked opportunity is energy efficiency. And this is a slide from Rocky Mountain Institute and quoted from Amory Lovins, where he shows that energy efficiency from 1975 to 2007, I think it was, 2010, or 2017, the energy was cut in half from a GDP standpoint. And it's predicted that we will more than cut it in half going out to 2050. So this is a huge step in the right direction. And a real theme in this talk today is how important energy efficiency first is to solving or getting to our goal of a net zero carbon emission future. So flip to the next one. And our grid, as many of you know, is being transformed. The old grid was, over 100-year-old technology, was designed for electricity to flow in one direction. It was generation. This is generating electricity from fossil fuels, was typically in the 30 to 40% efficient. So 30 to 40% of the original energy was converted to electricity, and the other 60 to 70% was converted to heat, which is why so many power plants are along lakes and rivers where they have a heat source, heat sink, I should say, to dispense of the excess heat from generation. And when you include transmission, typically electricity out of every 1 unit of energy at the site, it takes 4 units of energy at the source to create that. So a very inefficient systems. It's important to note that if you look at it from a site perspective, currently every 1 unit of energy you save on site will save 4 units of energy back at some source. Flip to the next one. So the smart grid of the future is being redesigned for bidirectional flow of electricity, bidirectional flow of information, and it's designed for local generation of electricity, reducing peak demand intelligently because there's communication between both source and load. And it's designed to be integrated with electric vehicles and battery storage where charging would occur during low demand periods. Go ahead and flip. And back to the topic of energy efficiency doesn't always cost more. The conventional wisdom is that you get your biggest bang for your buck in the first inch of insulation, for example, and every inch after that, there's diminishing returns, but linear cost. And this is a scatter plot. Again, this was produced by Rocky Mountain Institute, showing real case examples where with new buildings, you could see that way over on the x-axis of that graph is energy savings relative to a baseline, and on the y is a relative cost. And you can see that way over to the right, there are some strategies that achieved, significant over, close to 90% reduction in energy with relatively low cost. And the same thing was true on retrofitted buildings. You can ask yourself why. Well, part of it would be that by maybe improving the envelope to such a degree that the mechanical system ended up becoming way smaller, and reducing the cost of those systems paid for the envelope improvements. In retrofitted buildings, it could be planning such that when, let's say, that major central plant is due to be upgraded, you coincide with a lighting retrofit or other retrofits that makes the new equipment that's replacing the old significantly smaller, so that you offset some of the costs for, let's say, the thermal upgrades with savings on the mechanical or electrical side. So go ahead and flip. Now this is a bar graph from a remote campus that we initially studied and have since, we're about 80% through the retrofit, where the campus's goal was to meet net zero from a site perspective. And so the first bar on the left shows what their energy usage was when we first studied it. And the middle graph shows the energy usage that we were projecting we could get it down to cost effectively. So it's a 63% reduction in energy. And the right bar graph shows renewable energy to where we were basically trying to get these two to net out, the renewable energy on a seasonal basis, netting out with the energy being used by the building on a seasonal basis. But a real key to making this cost effective was the energy efficiency piece. This particular site, was had a large couple 100-acre site, and it was an excellent site for wind energy and solar. And so we are just in the last phase of finishing all the energy efficiency measures and are on track. And the renewable energy is now being planned. So flip to the next. This, we're going to give an example of Chicago Public Schools later, but initially we were part of a team that was asked to look at new Chicago Public Schools and how could they meet net zero from a site perspective. And typically in an urban environment, the only choice you have for renewable energy would be putting solar panels on the roof. And so if we wanted to basically make it net zero on an annual basis with solar energy, and we only had a limited amount of roof area, we would have to get the energy usage of the building down so that it was equal or lower than the amount of energy we could produce from roof-mounted solar cells. And you can see in this one example, the International Energy IECC 2015, if we applied that particular standard, there's no way that the building, there just wasn't enough roof area to be able to meet net zero. But if we design the envelope to meet a passive house standard, much more stringent standard, then all of a sudden we could achieve. So the point again being is what are your available renewable energy sources, and just how efficient you have to get the building to make it, to make it balance. Go ahead. And so thermal envelope is huge, and passive house standard, one of the requirements to be certified is a commission building that meets some very stringent air tightness requirements. And with a blower door test, it's usually, or you're pressurizing the building up to 50 pascals and then measuring the amount of airflow that it takes to get there, and that's correlated, of course, with the amount of leakage of the building. Obviously, the importance of well-insulated roofs, some green roofs shown in the picture, the importance of a thermally broken envelope. This not only thermally broken window frames, but the thermally broken walls and roof and so forth. And another building we were involved in, a huge amount of effort went into just some masonry anchors that would hold the structure together, but would not transmit thermal energy through the anchors. Was a big topic of planning and discussion as we were planning the building. And of course, fenestration it's often estimated about 50% of the building lost in buildings is through the fenestration, with the potential low E, with low E glass and the selective coatings on the inner layer of glass, where basically it'll allow the shorter frequency winter sunlight to come in and add warmth, but will reflect the longer infrared waves from radiant energy generated from warm bodies within back in, or reflect the summer sun that's reflected off the pavement and other things back out, has made a huge difference in terms of the efficiency of windows, besides improving U values through double and triple glazing with special glasses in between. Go ahead. And of course, another thing would be, we try and recover energy wherever we can before it's rejected. And the example on the left, of course, is thermal energy wheels that are capable of recovering up to 80% of the energy from exhaust air to precondition your outside air. This has certainly become more important with a huge emphasis on indoor air quality that's as a result of the pandemic, so that we're not paying a huge penalty for that, increased amount of outside air that is required. The heat recovery example on the upper right is basically using, as a refrigerant system where you're recovering the condenser heat to preheat domestic hot water. The example down on the bottom is basically where a wrap on drain systems from showers, where you're preconditioning your hot water by recovering heat that is being rejected from shower heat. And continue. And another big challenge is that, particularly here in Chicago, where we're in a very cold climate, and probably 80 or 90% of all the heating in Chicago area is done with natural gas. And with the there's what do you do with the emissions of natural gas? And there's various campuses have talked about renewable gas, which is basically a biogas that is called renewable because the claim would be that the amount of the green plant life that is used to harvest and produce the biogas basically absorbs about the same amount of CO2 as the burning of the biogas emits. But it doesn't account for methane leaks, which there's always going to be methane leaks. And biogas is not that readily available, and it's expensive. So it's really not a long-term solution. And the solution of electrifying heating source, if you're looking at electric resistance heating, which is basically by definition has a COP of 1. This is a extremely inefficient way of heating. But there are other ways to heat buildings with electricity that are much more energy efficient. And generally they're heat pumps with a ground source heat pump, which typically has a seasonal COP of 4. That means it uses only 25% of the energy that electric resistance would use, and would be actually more cost effective than just from a dollar standpoint than heating with gas. The challenge with ground source heat pumps in existing buildings is where do you put the field, and do you have the available land area in an urban environment? Often you don't. And but air source heat pumps have come a long ways, particularly in the last 5 years. And many of you are familiar with variable VRF, variable refrigerant flow systems. And they're not as efficient as ground source because essentially a heat pump is extracting heat from the outdoors and pumping it up, basically it's using a thermal pump, a compressor to pump that heat uphill, if you will, and reject it inside. And the steeper that hill, the more energy it requires. So as it gets colder and colder outside, the efficiency and the output of a air source heat pump goes down, whereas a ground source, the deep ground temperature is pretty much a steady 54.5 degrees, which is primarily why ground source heat pumps are more efficient. But with recent advances in air source heat pumps, they have gotten to where they work down to -10. And by making the building weigh the envelope super efficient, we have successfully designed many systems that heat the building fine in the coldest Chicago weather without without a backup system. And there aren't that many really, really cold days. And so when you, the average winter temperature in Chicago is somewhere around 37, 38 degrees, and 37, 38 degrees, the efficiencies of air source heat pumps are very good. And so this is a way better solution than trying to heat with electricity, with electric resistance heating. But as we'll talk about later, it's going to be very important to improve the thermal envelope. And I'm going to switch it over to Brian, and we're going to talk about Christopher School at Chicago Public Schools as an example.
Great. Thank you, Don. So we're going to talk about Christopher School. Don had mentioned before that we did evaluations with the Chicago Public School System for understanding how they can make their buildings net zero. And it led to an opportunity to evaluate some of their existing buildings, Christopher Elementary being the primary evaluation that we performed. And how do we take an existing building, which, you know, the CPS system has a lot of property. So this presented a great opportunity and really work to improve it through the modeling process, and we'll talk about that. But just to give you an idea of Christopher Elementary School, it's a 1930s era construction, you know, built during the Great Depression. It's a pretty typical size at about 65,000 square feet. The school actually was originally built and currently serves students with special needs. So it was very important for us to you know, provide a nice, comfortable environment and be cognizant of the students' needs as part of this exercise. The building has a steam radiant system that was original to the building. The boilers had been replaced in the 90s, but the vast majority of the steam system was intact. And this included the makeup air handling unit. It was original, so it was a 90-year-old air handler, still in operation. However, you know, we found that it wasn't entirely sufficient for a modern HVAC system. There had been various roof top units that have been installed over the course of several additions. And some of the newer additions from the 70s and the 90s were installed with electric heat. So they didn't extend the steam boiler system to serve those portions of the building. They just installed electric resistance heating coils to serve those areas. So the first step for us was to evaluate this building virtually. We took the building and modeled it and calibrated the energy model to match with the utility bills. So we had a very accurate representation of how the building performed. And this allowed us several advantages when we were evaluating, you know, different improvements for the building. So we went through several different iterations. Here's a number of different iterations all the way on the column on the left. We have how the building performed. We found that it was about 100 BTUs per square foot. We evaluated various different improvements, including upgrading the entire envelope of the building, upgrading lighting. The last three columns on the right-hand side are three different evaluations of different HVAC system upgrades in combination with envelope upgrades. By upgrading the HVAC system to primarily a VRF system, DOAS, air source VRF, we found that we could get the building down to an EUI of 31. We evaluated both geothermal and traditional systems as well, and obviously with the geothermal system performing the best at 20.
I might add, Brian, that you can see in red, that's the energy associated with heating.
Right.
So you can see how important heating was to the energy performance of this building.
Right. And furthermore, by utilizing a geothermal system, we're able to completely eliminate any source of fossil fuel heat. With air source, we're unable to do that. The makeup air unit, several other air handlers did need to remain gas-fired. However, as you could understand, a geothermal system on an urban site does present challenges. While we felt we would be able to provide a geothermal system by utilizing area around the building in a remote parking lot. We found that the cost was quite expensive in order to do that. And the table at the bottom, you'll see we also provide the effect of carbon emissions. Now, keep in mind, this evaluation considers carbon emissions with our current electrical system, and with advances in renewable energy and upgrades to the electrical grid. The carbon emissions due to electricity is going to go down, while natural gas will stay the same. Our evaluation was projecting what we could provide to the building in the future. While we did evaluate implementing all the upgrades, we found that the budget only allowed for select upgrades, and the upgrades really focused in the primary core of the building that was most original and in the most need of attention from HVAC upgrades, and we had some limited level of envelope upgrades. We still were able to provide the building with an air source VRF system, which is what's had been designed and is being installed this summer. However, we needed to do a few considerations in order to do that. With a complete envelope upgrade, with replacing the windows and adding insulation to roofing in the attic, we would have been able to serve the building entirely off of an air source heat pump system. Because we didn't have the budget to do the window replacement and some of the other envelope upgrades that would have been required to have the air source VRF system serve the building, we had to be a little creative, and what we did is design the air source system being cognizant of what those future upgrades are. So when they are able to replace the windows and add that insulation, that the air source system on its own would be able to handle the building, down to -10 and below. However, due to the D rate of the VRF systems, at very low outdoor ambient temperatures, we needed to provide supplemental heating at certain times of the year. So the way that the HVAC system is designed right now for the building, we're able to operate entirely on the air source VRF system down to about 10 degrees. Below 10 degrees, we transition over to the existing steam radiant system. So we're able to utilize existing infrastructure while providing this upgrade. And in the future, when they are able to do further upgrades to the building, they can entirely decommission the steam system. The building had pretty advanced systems considering its age. The makeup air unit was designed in such a way that it did provide ventilation low. So areas of the building we were able to upgrade into a displacement type system. If you see the picture on the top, that's their auditorium. Those little squares on the floor are actually the diffusers, so air's supplied low. We were able to upgrade those diffusers into a displacement style system to better provide air conditioning to that space and keep the supply low and limit the space conditioning to the lower level of that auditorium. Right now, that space has a couple of window units that really are insufficient.
I might add two benefits of displacement ventilation is one, by supplying fresh air low, you're getting the air into the breathing zone much more effectively.
Right.
And also by allowing the hot air to just rise and stratify, you basically are not cooling that upper layer of air to the same degree that you are the air that is in the people zone, if you will. And so it also, it's more efficient from that perspective as well.
Right. You know, so we really wanted to utilize existing infrastructure where it made sense to, and you know, some of the features of the building were, you know, did allow us to provide for, you know, creative solutions. Fortunately, this building had a pretty beefy attic. If you can see on the picture on the lower left-hand side, if you're able to duck, you can walk through the attic. This allowed us enough room to distribute DOAS air because we weren't providing the space conditioning to the all the various classrooms and offices. That attic was sufficient for you know, the smaller duct size that would be required for dedicated air. Part of the strategies we implemented is demand control ventilation. Certainly, this the strategy makes a ton of sense, especially when you have a DOAS system. It's very easy to control. We're able to modulate the supply air into each of the classrooms entirely based on monitoring the CO2 levels in the space. We paired that with energy recovery on the DOAS systems to really reduce the amount of natural gas that we required. We do have an air source VRF system, as I had mentioned. The air source VRF system does have the simultaneous heating and cooling, and it does improve the efficiency of the VRF system, especially during the swing seasons when some spaces are going to be in heating and others are in cooling, and you can transfer heat around the building. One other thing about the design is we were very cognizant of being able to provide heat to the space in the event of a power outage or you know, in the instance of a compressor failure. And we made sure that our DOAS systems were able to compensate, you know, in those emergency scenarios. Don had mentioned displacement ventilation and how that strategy really reduces the, you know, the demands on the cooling system by keeping the supplier air low and exhausting high. The heat that is generated stays up high. We don't have to cool that whole entire space. We just have to cool that lower portion of the occupied load. And then we just exhaust the heat. What was very important strategy is to implement a digital control system for the building. This allowed us to do the strategies such as demand control ventilation and schedule the equipment. So we're able to turn it off. The control system that Christopher currently has is all pneumatic and largely non-functional. In fact, the building engineer had to kind of time when he turned the boilers on and off in order to, you know, keep the building hot. And you know, and that obviously presents, you know, a level of you know, discomfort. Additionally, because the building had window air conditioning units, they had that potential for simultaneous heating and cooling as well.
So this is just actually a picture from a large geothermal system that we did. We didn't use geothermal at Christopher, but we've used it successfully in quite a few different applications in Chicago. One very recently where we ended up drilling a whole bunch of the wells underneath the parking garage before it was built, that the building was built on. So this actually is showing a vault where the main headers and there were 92 wells in this particular site that went down 500 feet. And it's about a 250,000 square foot building that is entirely heated and cooled, and the domestic water for dorm rooms is all produced through geothermal system. You go ahead and flip to the next. This is a recent study by Princeton, and so I'm kind of going back out to 30,000 foot level here. But it was extremely interesting. It's the most detailed study that I've seen to date that looked at 5 different scenarios at getting to net zero emissions by 2050. And basically you can see in that little basically Excel box on the left, it's showing you trillions of dollars and net present value, blah, blah, blah. But the reference would be, essentially a fossil fuel future. And they're assuming that fossil fuels would stay as cheap as they are today, which is an unrealistic assumption. But you can see that the cost of infrastructure going forward with this sort of unrealistic low price of future fossil fuels use of 22, and that's in $1 trillion over, from now until 2050. And the cost of the different scenarios to meet net zero is not that significantly higher. So if you flip to the next slide, this goes into more detail of each 5 of the scenarios. Some of them allowed nuclear power as part of the solution. Others did not. You can go to this, it's a 300-page study, but there's a couple of page summary. I just thought I'd leave this with you as, this is both achievable and affordable, and flip to the, and basically, our conclusion is that the technology exists today, reduce CO2 emissions and mitigate climate change. It's not any new technology that has to be invented to get there, although there will be technology that will help us get there more cost effectively as we move forward. And these technologies make sense even without considering the cost of climate change. So I just leave with a quote from Sheila, the president of ASHRAE: first we become aware, then we become engaged, and we start now. So with that, we turn it over for questions.
Thank you, Don. It was a great presentation. I would say this is an ideal scenario of making an existing building. Both work on the electrification and the reducing the energy in an existing building. So we have plenty of time left. When we had the pleasure of holding these events in person, we've been using all this time for the conversation and talking about the challenges and the opportunities that coming up in related to this type of projects. So if you have questions, you can ask, you can chat and ask your question there, or if you want, you can ask and we can unmute you and you can ask your question. And while we are waiting for some questions, I can ask the first question, which is, I'm interested to see that we are seeing a lot of like new construction that are 100% electric or pursuing passive house or pursuing net zero certification, but the main intent of the carbon leadership from that we are all talking about is to reduce and eliminate the embodied carbon. And like simply with working on an existing building, we are just like resolving the issue in the first place. I was curious to know if you guys done any analysis, some sort of whole building LCA or any embodied carbon analysis to show that with simply using an existing building and not demolishing the building and build another high performance buildings, how much carbon emission, embodied carbon emission we save there. Or that's one question. The other question is what was the intent of the client on pursuing this type of renovation?
Well, I'll just start with it. You know, as we mentioned a little bit, you know, and we were, you know, part of a team that initially with Chicago Public Schools. They were looking at upgrading their, you know, upgrading their standards for new buildings, but the whole team kind of got to the point where we realized that we'd have a much bigger impact on their portfolio going after, I mean, certainly the new buildings, but they don't build that many new buildings, and they have a huge portfolio of existing buildings. And you're not going to build your way out of this, you know. So I mean, the retrofit environment is a huge opportunity and is a must to reach the goals that of net zero carbon emissions by 2050. And we all have to remember the embodied energy and materials. I mean, concrete, of course, you know, the making of concrete is, you know, there's significant emissions associated with that. And existing buildings can be made to, you know, with new windows and new insulation and so forth, can approach the efficiency of new buildings from an envelope perspective. There's no reason why they can't. So I don't know, I'll leave that, you know. Brian, Dustin, do you want to?
Yeah, let me add on to that. I mean, buildings require maintenance constantly, and you know, the Chicago public school system's continuously looking at their buildings and having to do projects, you know, that are need-based. Christopher was entirely need-based. The ventilation system wasn't sufficient to, you know, what we would require now, and steps had to be taken. So, you know, this really presented a very intelligent way of looking at how to approach it by serving the building's needs. The building didn't need to be torn down. You know, the walls, everything was in great condition, but we had to do those upgrades. So the incremental cost of installing what they may have done as a standard versus upgrading to a higher efficiency type system really it's incremental. It's pays back, you know, very quickly, and they're continuously looking, you know, they're continuously going about that. So you have more frequent opportunities to be able to afford a new school is so much more expensive, and they're not, you know, going to tear down every school. So this is a very, very impactful way of just overall, you know, reducing their, you know, energy portfolio.
Great. We have a couple of really good questions. The first one is from Sarah. Sarah, I ask you to unmute yourself. If you can unmute yourself, you can ask your question now.
Sure. Can you guys hear me?
Yeah, we can hear you great.
Great. First of all, thank you guys for such a great presentation. And I thought the Christopher School, analysis was obviously super compelling and helped to make those decisions. I just wanted to make sure that I caught what the team was able to implement, and it sounded as if there were actually no envelope upgrades that were made. Is that right, Brian?
There were minimal. The idea would be that we would have replaced all the windows. We just weren't able to do that. We did have some, for instance, just taking out the window air conditioning units does reduce the infiltration. We did some roof upgrades as well, but the overall insulating value didn't really change. We feel that we were able to reduce the infiltration some. We also, with some control strategies, are going to positively pressurize the building that will further reduce the infiltration rates. However, controlling infiltration is a big deal when you want to use like a air source system down to -10 degrees. To be able to heat that space down to that temperature, you'd really have to oversize the system. It would have really added a lot of cost, and we felt would have presented some challenges to the existing electrical infrastructure of the building.
Right. Yeah, my company does a lot of work with historic preservation projects where there are, a lot of restrictions as far as what you can do to the envelope. And I often get confronted with those concerns that, we can't make, many envelope upgrades. So it's nice to see examples of projects that you can still make a considerable improvements with other strategies. So thank you.
Thank you, Sarah.
Great. Thank you. Great question. The next one is from Tom. Tom, I ask you to unmute yourself. If you can unmute yourself, great. If not, I can ask the question on your behalf. Oh, okay, you're unmuted. Yeah. You can go ahead.
Yeah, thanks, Mohammed. Yeah, I was just curious which refrigerant was used in this specific VRF system. Understandably, it's a net gain to go to VRF. There's ample gains on the source emission side, and it's an area that we don't give much thought to, but thinking about the embodied carbon footprint of pretty high GWP refrigerants today, just didn't know if that was sort of quantified or taken into account. There's Steve gave a good response there. I'm pretty well aware what's out there. Just was curious.
Well, of course, yeah. So yeah, everybody saw the little chat box, and thank you, Steve, for answering that question. And yes, I believe it was 410A, wasn't it, Brian?
That's correct.
Yeah, and it's important to remember that refrigerant, provided it doesn't, it stays within the system. And obviously these are hermetic systems that are, it's one of the most crucial parts of commissioning a VRF system is ensuring that before the refrigerant's even installed, you have a completely tight refrigerant tight system. So if the refrigerant's only going to harm the atmosphere if it leaks out. And so, through a lot of diligence and a lot of training, every effort is kept so that just does not happen. And but that being said, there are new refrigerants on the horizon, as Steve mentioned, that that for future systems that will that will have more choices.
one of the, this is Steve Kwiak, one of the interesting trends in Europe, because they're about 4 to 6 years ahead of us on the F-gas phase down, what we've been seeing is a trend away from larger charge systems like VRF, pounds of refrigerant per ton, just because of allocation issues. People look at it from a cost of refrigerant. Sorry, that was some ice. There is some regulation in some markets in Europe that are pushing people away from larger charge systems, but you can always adapt to that with a variable water flow system or something like that. So, I mean, I think as regulations come in, I think technology will adapt to reduce refrigerant charges as far as we can or technically possibly reduce. So,
well, in the city of Chicago, we are reduced to how many pounds of refrigerant? What is it, Brian?
You have to be below 100 pounds, or else they'll require just some significant upgrades to the system that are expensive.
So this system was obviously designed with each system below 100 pounds. Then. Yeah,
and there we do evaluate to make sure that refrigerant concentrations do not exceed the ASHRAE 1534 levels as well. So in some instances, we'll be below that threshold, depending on the volume of space that the pipes are running through and what they serve, rooms they serve.
Yeah, and I mean obviously the negative trade-off to trying to make that even smaller would be that the heat recovery aspect of VRF, which is a significant benefit. It basically you've got the ability to move heat from a zone that requires cooling to a zone that requires heating, and it requires some. I mean, if you the extreme opposite example would be ductless splits, where you got one cassette and one condenser, and obviously you couldn't do heat recovery.
Yeah, it'd be interesting. I think that heat recovery more than offsets the refrigerant GWP, just because you're reducing the natural gas load, right, and carbon emissions from that. It'd be interesting though when you guys roll up your carbon use, you can roll up the refrigerant in there and just assume a leak rate per year, because these systems do leak on average over their life. All of them do, no matter how hard you try. There's always an example or two. So it'd be interesting to see to add that to your pile as you look at various systems and the impacts of the carbon.
Thank you. I mean, not to spoil the next event topic, but the next. No. I just wanted to mention that I'm so glad that this seems to be a really hot topic in the trend. So our next event that you're going to be seeing that soon is a panel on the same exact topic that we are discussing now, and Steve, Train, WSP, and Elara are going to be on the panel and discuss what is coming next and what are the trends that we have to catch up with. So, but yeah, definitely this is perhaps when VRF is a really efficient system, but comes with some challenges for sure. I don't see more question here. I had a follow-up question to what Sarah asked earlier on envelope, and I was curious to know if if you have done any type of energy cost measures for envelope improvements, and also for the infiltration that you mentioned. Like, that's always a challenge when we are doing energy model for existing buildings, because for new construction is comparative. We don't care much about the infiltration. We just use ASHRAE defaults, and sometimes for passive house, we change that based on the detail. But when it comes to existing building, is a different scenario because we can measure that, as you mentioned in the presentation. So I was curious to know what type of analysis you did with the energy model around infiltration, and also for envelope. Did you run any type of energy cost measures for the envelope parameters and discuss that with the client?
Yeah, no, absolutely. We you know, a lot of the analysis we went through did consider, you know, we did a calibrated energy model, and we did work through, you know, a lot of the infiltration rates that we felt were appropriate from what we were seeing. And we did run through a number of different iterations to zero that in and what would have been appropriate. We also had a number of inspections, and you know, we have a thermal imaging gun that we were really able to do, you know, certain inspections. The windows do not perform very well. It was quite clear that it's certainly a big source of heat loss for the building. The envelope improvements is really where we started. We went through, I think, 4 different scenarios of window improvements. The building has skylights as well, and we even considered upgrades to the skylights, using roof monitors also instead of just a pure skylight too. We tried to make decisions about whether or not to keep the skylights intelligently. There were some skylights over a bathroom, which really didn't offer much value. But the skylights in the corridors and the skylights that were over offices, you know, certainly we looked to upgrade those and improve the performance as part of our analysis. So our analysis, as we mentioned, did primarily focus in on the envelope improvements. Now, the windows had been last replaced, I think, in the early 90s. So they weren't necessarily due for a replacement. It had there been room in the budget, certainly they would have been replaced. However, they had a little bit of life left, so it wasn't, you know, set out as a specific need for the building. Again, our analysis, and especially with the design of the VRF system, we wanted to be cognizant of, you know, what type of system they would be, you know, providing down the road, which would really make these upgrades more affordable when they, you know, do some of the other envelope improvements that we had prescribed. They'll be able to completely decommission the steam system with a few modifications, of course.
Great. Do we have more questions? I don't see more questions in the chat box. I wanted to mention that this event was organized by CLF Chicago, and CLF Chicago, it's a small team of architects, contractors, and engineers, similar to the CLF National. And it's me, David Swain from Studio Gang, Emily Purcell with SCB, and Juanita Garcia with Pepper Construction. If you also have something, Emily, David, Juanita, if you have anything to add, feel free to unmute yourself and chime in.
Thanks, Mohammed. I just want to thank both Brian and Don for being here today. And I think it was a very poignant presentation. And yeah, I look forward, obviously, to hearing more from them and their great work that they've done.
Thank you.
Thanks, David.
Yeah, same here. Thank you too. Definitely appreciate hearing, what can be done with these really inefficient historic buildings that we have quite a few of in Chicago. So it's yeah, great insight on that.
Thank you, everybody.
Hey, Brian and Don, actually, I did have a question for you. And maybe I missed it at the beginning, but are either of you involved with making any upgrades to the Chicago Building Code or to maybe to ASHRAE? Are you personally involved?
Yes, we are. You know, I mean, that's all, it's a committee process, as you know, but yes. Dustin, who I think is still on the call, is also very involved in ASHRAE.
Right. Now, we need big changes, and before 2040.
Yep. Yeah, absolutely.
Yeah.
Yeah, I mean, this was a great presentation and great projects. And one more thing that I would add was really impressive was the fact that electrification and reducing carbon doesn't necessarily need to happen in projects with massive budgets, or just like projects that go under like a new construction. This was a really good example that we need to tackle a bigger part of the market that is causing or just emitting a huge carbon to the atmosphere. So yeah, I hope we see more of these type of projects. And once again, I thank Elara for such a great presentation. Our next event gonna be on a panel on refrigerant, and I was so happy to see that was naturally happening, and that's a great topic and an interest of the people in the call. So I would invite you all to attend. If there's no more question, I think when we had, again, we have 18 minutes left. We used to use this time for networking and socializing. When we were doing them in person, I'm sure none of us had that pleasure in the last year or so. I think we can wrap it up sooner, or if we can continue the conversation. But our Q&A and the presentation is done, and I thank you all for attending the event this afternoon with us.
Thank you.
Thank you, Anna.
I'm going to
Thanks,
bow
everyone.
out. Yeah, okay, thanks.
Thanks all.
Thanks. Have a good night.